So today is our last lecture. In 2 weeks we're going to have a final exam. And I want to finish with, I want to finish this chapter with one general thing, so definition and then a proposition. And then we're going to discuss with more detail sexts and tors. So definition, an object, and in our case just a module, but this makes sense in any abelian category. An object is called f acyclic. So I continue to assume that the f is just the right exact functor, so we can define left to right functors. And there is, of course, the same definition in the case when f is the left exact and for the right derived functors. So if all derived functors on this object Q, so let me call this object Q, are isomorphic to 0 for all positive indices. So on the second part of the definition, and f acyclic resolution of A is the left resolution so I'm going to call this Q with a dot of the object A, such that all objects Qi are f acyclic. Or any I greater or equal to 0. So that's just a straightforward definition, and the main example, at least in this elementary course, is the following. We can consider as a functor f, which is a tensor product, say with some given module m, so that's a functor, and then f acyclic modules are by definition flat modules. So, and why this notion is important? Well, because actually you can use these acyclic resolutions to compute the derived functors. So we define, for example, in this situation we talk about left derived functors. We define left derived functors using projective resolutions, but in fact you can use any acyclic resolution. For example, for this functor you can use a flat resolution, so just a left resolution such that every module is flat. So that's the next proposition. So if we have Q, which is an f acyclic resolution, so then the left derived functor with the index n is the same as the nth homology, so isomorphic to nth homology of the functor f, which is applied to the acyclic resolution. And that is for any n greater or equal to 0. So which indeed just says that you, instead of using just projective resolutions, you can use any acyclic resolutions. In this case, that would be flat resolutions. So proof is more or less the same as the dimension shifting at the end of the previous lecture. So based on more or less the same ideas. So I want to introduce syzygies for the resolution Q. So I have short exact sequences Ki plus 1, Qi, Ki minus 1. Right? So I have this exact complex. I can split this into such short exact sequences. This is of course for any I, say for any I which is at least 1, and of course as usual I assume that the K0 is the same thing as A. So then the argument that we use for the dimension shifting, now just looking at the, take this short exact sequence and look at the corresponding long exact sequence of the left-derived functors, the same works here since Qi is acyclic. So the conclusion is that the left-derived functor with the index n on object A, sorry, that's okay. So on the, not A, but on the Ki is the same as the L with the index n minus 1, F applied to the Ki plus 1. So we still have this dimension shifting, but for the acyclic resolution. And in particular, if you iterate this construction several times, you'll get the formula that the nth derived functor on the object A is the same thing as the first left-derived functor on the syzygy with the index n plus 1. So next we will look at the commutative diagram. So beginning of the resolution, so Q2, Q1, then this is mapped to the K1, 0, and here I have Q0, Q0, this is just the identity, and let me call this map the embedding little I. So to this diagram I'm applying functor f. Then I want to use snake lemma, so I want to keep some space for the kernels. So I will get f of the Q2, f of the Q1, f of K1. Right, so this is exact, since I assume that the functor is right exact. Well, and of course this is mapped to the f of the Q0, f of the Q0, and this is just an isomorphism, and also there is a map f of I here. So I can add 0 here, get the corresponding short exact sequence, kind of the trivial one, with just isomorphism here, and this is just a 0 object. And then I apply the snake lemma. So kernel here is very easy to compute. This is f of the Q2. Now the kernel, so the next kernel I'm just write as a kernel of the f of the differential. Right, so this map from Q1 to the Q0 is just the first differential. So this is just f of the d1. Oh, then there is the next kernel, but I can claim that I can immediately compute this and say that this is L1 f of A.
Сейчас можно вопрос, а вот в точной последовательности сизигиями разве не должно быть плюс 1 и появится?
И... Да. Да. Yeah, but the next line is correct. Yeah, so here I'm going to computing the kernels. Well, since at this position I have 0, there is no kernel, it's trivial, so I can also write 0 here. So the question is probably, the only question is, how do I know that this kernel is just the first left-derived functor? What's the argument? Oh, it's the same as before. So if you want to understand the kernel of this map, you look at the short exact sequence. The first one in this series of sequences, you have K1, K0, A, and then since K0 is acyclic, you get a 4-term exact sequence right? So that's the beginning of the long exact sequence, but the next term, which I'm supposed to put here, will be the left-derived functor with index 1 for the object Q0, which is 0. So there are, at least, well, there's this sequence with 4 terms. And in particular, we can see, of course, this is just the embedding, so this is the same little I. So we can see that the kernel of this, and this will be f of the little I, so the kernel is precisely the first left-derived functor. So the conclusion is from this commutative diagram is following: H1 of the f q is isomorphic to the first left-derived functor applied to the object A. And then we just used again the kind of the dimension shifting. If I want to compute the left-derived functor with the index n, well, first of all, I use the dimension shifting that I know works for the derived functors. So this is first left-derived functor for the kn. Is this +1 or -1? Okay, +1. So then, since now this is just the first left-derived functor and we have the previous result, I can write this as the first homology and functor f applied to the this exact sequence, right? I'm just computing the H1 first homology, but for the object k with the index n +1. But if you just look at what you do, at what position you compute this first homology, well, namely you compute this at this position, that is the same thing as the computing the nth homology of the f applied to the q. So that's the end of the proof. Okay, so section 4.5, extendor. So theorem. So sometimes this is called balancing Tor. And this might be one of the most important properties of the Tor in the elementary homological algebra. So the statement is the following. So let P be projective resolution of the right module A. I'll continue to use projective resolutions, but since we know the previous result, I can as well use flat resolutions. So let P be a projective resolution of right module A, and Q is a projective resolution of the left module B. So then, the Tor with the index n between modules A and B, which we defined as the homology, where you replace the first argument with the resolution and keep the second argument. Well, this is not a statement, this is just a definition of this Tor n, right? So, but I can as well compute this. So this is isomorphic to the nth homology. I keep the first argument, A, and use the second resolution Q instead of the second argument. So this means that this Tor n can be computed with any resolution, with the projective resolution of the first argument or projective resolution of the second argument. And for this reason, this is called the balancing of the Tor. So balancing Tor, balancing of the Tor. I'm not sure what is the right way to say this. So let me, for the convenience of the proof, also call this this homology, when I resolve the second argument, Tor with a little t. Just notation, temporary notation for the proof of this theorem. So no matter how you define, no matter which argument you resolve, you'll get the same derived function. Okay, proof. Again, I want to introduce syzygy short exact sequences. So 0, ki, pi, ki minus 1. So these are syzygies for the resolution P. And as usually, I assume that the k0 is just A. And notation for the syzygy in the resolution Q will be V. So 0, V, say with the index j, not to confuse two indices, mapped to the Qj, and this is mapped to the V, j minus 1. And again, V0 is by definition B. Okay, so on the next step, I need to draw a large diagram. So I'm going to use this blackboard for the diagram and the previous blackboard for some computations. So I want to take these two short exact sequences and take it as a product of them. So we have ki tensor Vj. This is mapped to the ki tensor Qj. Ki tensor with V j with index minus 1. So then the next is pi Vj, ki minus 1 tensor product with Vj. Okay, so this is a 3x3 diagram, and you can see the idea. If you take a tensor product, for example, well, if you look, for example, at the first row, this is just the short exact sequence of the second type, but I take a tensor product with ki. So all the maps are induced by the standard tensor product of the maps in the second short exact sequence with ki. So the same is for the second row, right? I just again take this second short exact sequence, take a tensor product with pi, and this tensor product with the ki minus 1. And the same is true for the columns, right? So if you look at any of the columns, so for example, this will be the first short exact sequence tensor product with the Vj, and the same is here. So of course, since the tensor product is right exact, we have zeros on the right, and by the same logic we have zeros on the bottom. Okay, but then, well, we also have 0 here, right? So this is exact, since I take a short exact sequence and I take a tensor product with pi, and pi is projective, and any projective is flat. But on the other positions, I have something. So let me introduce notation for this something. I'm going to call this object Z, and this will be by definition the kernel of B. So B is this map, and Z is just the kernel of the B. So here I'm going to call the map A, and it also has some kernel. I'm going to call this kernel Y, and the also later for the computations I need the a name for the map for the embedding. This will be a I sub y. And also this square is commutative. Why this square is commutative? Oh, just by naturality. We spent a lot of efforts last time to showing that everything is natural. So in this case, this is natural diagrams. So all the squares are commutative. And the same as I can apply here. So let me call this map F. So then the kernel I'm going to call X. And the embedding map I with index X. So here, of course, the kernel is 0 by the same reason as before. I have short exact sequence, take it as a product with a projective module. So this square is also commutative. And yeah, the last one, the map is going to be H, and the kernel of this map is W. So this is kernel of H. So that's the diagram that I need. And now some computations. Well, I have Tor1 between objects k with the index I minus 1 and the object v with the index j minus 1. Right, so first of all, we can notice that we can find this Tor1 on the diagram. And so this Tor1 is precisely W. Why is that? Again, you look at the short exact sequence, in this case ki, pi, ki minus 1, you apply the tensor product, you draw the long diagram of the torus, but since this is projective hence flat, again you get just 4 terms, so there will be a kernel which is W, and that's precisely the Tor1. So Tor1 I can identify with the W. And then I also claim that the W is the same thing as the Z. Right? To understand that W is isomorphic to Z, well, you do the following. You, for example, isolate part of this diagram. So you look at this part of the diagram. And to this you can apply the snake lemma, right? So applying the snake lemma, well, it tells you, well, since you have 0 here, that you have this kernel, and this is mapped to the corresponding co-kernel, so the co-kernel is here and here, right? Maybe it will be easier to see if I just write this. Snake lemma tells you that you have W, and then you have ki minus 1 tensor product with the Vj, ki minus 1 tensor product with the Qj, I minus 1 tensor product with Vj minus 1. Right, so that's the snake lemma for this diagram. But it means, well, it means that if I look at this map, its kernel, well, this is just map B, so its kernel is by definition is Z. So Z is the same as W. So W is isomorphic to the kernel. So I can identify this with the Z, but for the same reason as I have the first identification, Z is the same as the Tor1, but with a little t, all between objects k I minus 1 and v with the index j minus 1. So we just need to find this Z on the diagram and use the same argument as before. We look at the corresponding. So here I'm keeping first argument just ki minus 1. So applying this with to take a tensor product with a short exact sequence, Vj, Qj, and Vj minus 1. And since Qj is projective, the long exact sequence of the torus, it just will be a 4-term sequence, and the last term will be Z, or also Tor with a little t. Okay, so we have these identifications. This is the first step in the proof. Now, I also want to show that X is isomorphic to the Y. Well, it's a little bit different computation, maybe even easier. So what's Y? Well, first of all, this is kernel of the map A. right? Which I can write as the image of the embedding, I with the index y. Well, and then I claim that this image of this embedding is a submodule inside the kernel of the map F, right? So this is inside the kernel of the F. And this is because the square is commutative, right? The composition of the I sub y and F is 0. So we have this inclusion. Now the kernel of F, I can also identify with the image of the I with the index x, well, just more or less by definition, of the ix. And now this image is sub-object inside the kernel of the A, of the map A. And this is again looking at this commutative square, so this composition is a 0 map, hence the image of this map is in the kernel of this map. So we kind of have these inclusions. Yeah, and also we can notice that the image of the ix is precisely x. So we have y sub-object in the x and x is sub-object in the y. So there is an isomorphism of the x and y. So these two things are also isomorphic. Now, what are x and y in terms of the derived functors? So the x is tor1, and the arguments are k with the index I minus 1 vj. So this is x. Again, we need to look at the diagram and realize that this is another instance of this 4-term exact sequence. And so I can identify this with a y, and y, again, by looking at the diagram, is isomorphic to the tor1 with a little t for the objects ki and vj minus 1. Right? Again, find y, 4-term sequence, give you this. So we kind of have this relation between tor1, 2 arguments with the indices, and tor1 with the little t, 2 arguments with the indices. But you can see that you can move this minus 1 from the first argument to the second argument. So that's the result of the second computation. So finally we can combine this all together. I look at the tor with the index n between a and b. By the dimension shifting for the first argument, I can write this as the tor1 syzygy with the index kn minus 1 and then b. Now I can use my previous computation and move this minus 1 several times and get tor1 between a and v with the index n minus 1, right, which can be identified with the tor1 a v n minus 1. And finally, by the dimension shifting, this is tor with a little t and index n between a and b. So that's the end of the computation and the end of the proof. Doesn't make sense, this last computation? Well, first I do the standard dimension shifting, right? Reduce the derived functor with the index n to the first derived functor and the corresponding syzygy. So then on the next step, I use my previous computations. First of all, I know that I can identify when the index is just 1, I can identify if the arguments are the same, then this tor is the same as this tor with the little t. So in the next computation, right, which I do here, I use the previous computation where I can move this minus 1 from the first argument to the second argument, and I also know when the index is 1, there is no difference between tor and tor. So hence I get this. And then the rest is just, again, the dimension shifting. Well, no, well, first of all, here I use that for the first index, the tors are the same. And then the last isomorphism is just the dimension shifting for the functor little tor. So quite straightforward computation, actually, if you think about this.
Можно спросить, а как мы получили изоморфизм Tor1 K-1b и Tor1 V1?
I mean, this one?
Yes.
Well, as I just explained, so by the previous formula, I can move the minuses from the first argument to the second argument.
But that is small t, right?
Hmm?
But that is small t, so can you explain the third tor, like tor1k vn minus 1? How does it come?
You're still asking about this isomorphism?
Yeah.
Well, this is just this. Well, you can look at this formula, also combine this with this formula. So it means that, for example, here I also can write the tor with a large T. That's still true. So this is why I can write tor with a large T here and here. And then, well, you just use, well, so here, for example, in this formula, since we know that the V0 is the same as B, right? So here you can plug in that you have something like V0 here, and then there is this thing. So you can, so you can increase the index of the first argument, right? So, or maybe I can use this the other way around. So maybe, well, first of all, this can be identified with the tor 1 Ki Vj minus 1, right? So yeah, maybe I'm using, I think, from the right hand side to the left hand side. So here in this thing, I want to increase the index of the second argument and decrease the index of the first argument. But I can still do this while just reading the same formula, but from the right to the left. And then I do this several steps. For example, here I have V0, which is B. On the next step, I'll get V1, increase this by 1, but decrease this by 1. And then I continue doing this several times until I, well, reach Vn minus 1. So I'm doing this n minus 1 times. But it means that here I also get A.
И можно еще один вопрос? Как вы получили компетентность квадрата Ивы в тензорном произведении?
По естественности. Ну, мы доказывали, что если у нас есть как бы две короткие точные последовательности, морфизм между ними, мы смотрим на длинные точные последовательности, соответственно, производных функторов, то там все возникающие квадратики у нас будут коммутативные. Да, но это просто вот частный случай, здесь просто один квадратик всего нужен. Okay, and there is another theorem of the same type. This is called the balancing of the X. The proof is more or less the same. At least the logic is the same. The detailed computation is a little bit different. So let me call this theorem with the prime. So here assume that I have P, which is a projective resolution of module A. And I also have injective resolution for the module B. So this is injective resolution. So then the result is more or less the same. You can take the X with the index n between A and B. So we define this to be the homology with the index n of the hom from A to the injective resolution. Remember that we define this to be right-derived functor, right? So it means that I need to replace the first argument is fixed, and I need to replace B with the injective resolution. And so again, this is just definition, nothing happened here, but this is also isomorphic to the nth homology, nth cohomology of the hom between the projective argument of the first argument, projective resolution of the first argument, and I fix the second argument. So the statement is again saying that, well, this is balancing of the x. You can use projective resolution of the first argument, right? Compute the hom between resolution and the b, take the homology, or you can use injective resolution for the second argument, and the answer is the same. Doesn't matter what you use. So, and again, well, you can, I'm not going to do the proof because the proof is more or less the same. I'm going to leave this as an exercise. Well, for example, you can temporarily introduce notation that this is x to the little x and do the same computation. So you need to write the two short exact sequences corresponding 3x3 diagrams, but instead of the tensor products, you'll get homs, you'll get exactness not on the right but on the left, you get some non-zero objects, and you do kind of similar computations and get the result. But that's kind of important, right? Because in many, well, injective resolutions are hard to construct explicitly and hard to get an explicit answer for the x. But in many cases, much easier to understand the projective of, say, free resolution of the first argument. So from practical point of view, this is a very useful statement. Okay, so next thing I want to explain is the relation of the ext1 and extensions. And this is, I think, historically is the reason why we call this functor ext. So ext is just the beginning of the extensions. So first I need to define extensions. So definition. So suppose I have two modules. So definition with several parts. So in the first part I say that I have modules A and C. So these are some modules over the ring R. So an extension or to be more precise, this is extension of A by module C is just a short exact sequence A, B, C. So that's the definition of the extension. Then there is a notion of the map of the extensions. So morphism let's call this gamma. So this is just a triple alpha, beta, gamma. So from the one extension to another extension. So this E and E prime are two extensions. And on the diagram, this just means that I have one extension and another extension with the primes. And then there is map alpha, beta, and gamma. And two squares that we see here are commutative squares. So it's a very straightforward definition of a morphism of two extensions.
What are E and E
Hmm?
prime? What are E and E prime?
So E is this extension, and E prime is this extension. Okay, so part 3, two extensions E and E prime are called equivalent. So notation is the standard one. So if there is a map of the extensions gamma such that I have well, identity, well, some map which I'm going to call beta, and again identity. Right, so this is definition of the equivalent to equivalent extensions. Of course, you can notice if you apply the snake lemma that in this case beta is an isomorphism. And finally, for X CA is the set of equivalence classes of extensions.
Об этом не обязательно изоморфизм.
Я же объяснил, что это само собой изоморфизм. Просто следует из того, что написано уже. Okay, so now I have two goals about this X set. So I want to show that this X, note that this is X without indices. So this is just kind of a new definition, new object. So I want to show this is not just a set, but this is an abelian group. It has a natural addition. And also I want to show that this X, so the extensions are precisely the same thing as the X1, as I have in the title. So that would be kind of interpretation, at least for the X1. But you can, if you work a little bit harder, you can get the same interpretation for X with any index. You just, for the X2, for example, you need to consider 4-term complexes, and you can still define the addition on those complexes and show that such complexes are, or the equivalence classes of such complexes as an abelian group is equivalent to the X2. But if you get the idea for the X1, the generalization, I think, is not that hard. It's just a technical work. Okay, so I start with the lemma. So suppose I have an extension. So I have E, which is an element in the X CA. And I have a map gamma, just a map of modules from the C prime to the C. So then, there is a unique extension E prime that lives in the X C prime A. With morphism gamma, which is 1 some beta and little gamma. Okay, so given one extension and a map, I want to construct another extension. So let me draw this extension. I have 0, A, B, C. Right, so then there is C prime, there is a map gamma, and essentially what I'm trying to do, I'm kind of take this short exact sequence, take a map and kind of pull it back along this map and get a new short exact sequence. Now there is a one straightforward thing that you can do, right? So you have this map and you have this map. What you can do is you can form a pullback. At least this give you a commutative square here. So let me start with this pullback. So take a pullback of the B and C prime over the object C. And let me call this maps, so let me call the maps in the given sequence, say delta and sigma, and then this will be sigma prime. And the map that I have here is map beta that I have in the morphism in the statement. Okay. Well, I think it's easy to see that this map sigma prime is an epimorphism, right? We'll just look at the how you can describe this pullback in terms of the elements here. So this is pairs of elements, one in the B, one in the C prime, such that the images under these two maps are coinciding. So hence this is epimorphism. And now and this extension is still supposed to have module A, the same module A. But, for example, using the universal property of the pullback, I immediately get a map from the A to this pullback, right? Because I have a map from the A to the B, which is just map delta essentially, right? And the map from the A to the C prime is just a zero map. Hence, there is a unique map here, and this composition that I obtain here by construction is 0. So the only thing that we can ask now, is it true that we have exactness at this term? Oh, and also you can see, since we have this is commutative square, that this map is also a monomorphism. And for the exactness, again, you think about the elements of this pullback as pairs of elements from the B and C prime, such that they coincide. Well, suppose you have something, right? Take such pair. Suppose that sigma prime is mapping this to the 0, right? It means that the it means that for the second element, gamma of this element is 0. Hence, since these two maps are the same, the second element, if you apply sigma, it will be 0, which means by the exactness of the given extension, which means that it's exactly elements from the A. Well, check this. That's elementary diagram chase. Okay, so this is the way to construct this new extension and the morphism of extensions. And also, you can note that such extension is unique. Well, for example, suppose you have another one. So if E double prime with the map gamma double prime 1 some beta double prime gamma is another extension. So this is say map from the E double prime to E prime. Is another extension. Well, you can just define beta prime from the B double prime to the B. Again, using elements, say by the formula, if you apply this to the some element B with 2 primes, this will be the beta with 2 primes applied to the B, and the sigma with 2 primes applied to the B with 2 primes. So then 1 beta prime 1 as a map from the E with double primes to the E, that's an equivalence of extensions. And hence, such extension is unique. So we can, since we have this lemma, I can introduce notation. So notation for the E prime that I obtain in the lemma will be the product of the extension E and the map gamma on the right. So you can take extensions and multiply them by the elements of the home on the right. But of course you can do the same with the product on the left. So that's the lemma prime with more or less the same proof. So if we have an extension E between C and A, and there is a map alpha from the A to the A prime, so then there is a unique new extension E prime. Well, in this case, I can also, using such notation, say that this is a product of the alpha and E. So, which is an element in the X C A prime. So with morphism, gamma, which has components alpha, some beta, and identity on the C. So it's more or less the same proof. You take the short exact sequence, you have a map now from A to the A prime, so there will be some map, something like this. and then you take push out instead of the pullback. Okay, so theorem. So the set of all equivalence classes of the extensions is an abelian group. And formula for the addition of two extensions is the following. You take the codiagonal map for the object A, you just take the direct sum of two short exact sequences as complexes, and you take composition with diagonal map on the object C. So that's the addition. The zero element is the splitting short exact sequence. Also, you can notice that you can write minus a short exact sequence, or minus an extension, as the product of the map minus 1 on the module A and the extension E. And finally, you have in these two formulas showing that you have some kind of distributivity. If you take a product of the alpha on the left and the sum of two extensions, you can open parentheses and write this as alpha E1 plus alpha E2. So there is also formula where you take the sum of two module maps, take a product with the extension, and again this is the same as the alpha 1e plus alpha 2e. And there are the same formulas when you multiply on the right. Say E1 plus E2, you multiply this on the gamma on the right, you will get E1 gamma plus E2 gamma, and E, you multiply this on the sum of the gamma 1 and gamma 2, you'll get E gamma 1 plus E gamma 2. Okay. Kind of trying to summarize all the properties of this abelian group in one statement. Okay. So we have, first of all, several rather silly observations which we're going to use as a building blocks for less trivial observations. For example, if you have alpha 1 and alpha 2, you take a direct sum of these two maps and apply the, well, take a product with just a direct sum of two extensions. Well, clearly, this is the same thing as the alpha 1 E1 direct sum with alpha 2 E2. And the same if you do this in the other order. So you take E1 plus E2. Я определил слева и справа. Ну, только что. Да. Это лемма и лемма-штрих. Одно из них для одного, другое для другого. Okay, so you take the sum of two short exact sequences and you apply the sum, direct sum of two maps on the right. And again, this is what you expect this thing to be. So in this proof, I'm going to leave several steps as easy exercises. I don't think that I really need to prove this, since this is, you just look at the direct sums and see that this is true. And also, you can notice that if you have any map, say alpha, from A to the A prime, then for this map, you have the following. The composition of the alpha with the codiagonal is equal to the codiagonal and the direct sum of two copies of alpha. So this is as a map from the A plus A to the A prime. Right? If you think in terms of the elements, this is completely trivial. But it's also true, say, in any abelian category, you can use universal properties to show this. And the same for the gamma. So if gamma is a map from the C prime to the C, so then we have a formula that the diagonal composed with the gamma is the same as the direct sum of two gammas composed with the diagonal. So as a map from the C prime to the C plus C. Okay, so then we can do the following computation. So, for example, consider product of the alpha and the sum of the gamma 1 plus gamma 2, E1 and E2. Right, so then this is equivalent by the definition of the addition of the two extensions, alpha codiagonal E1 plus E2, and then diagonal. Right. So then, using one of the identities, I can write this as the codiagonal alpha plus alpha E1 plus E2, and then codiagonal, diagonal, and this is equivalent. So this is equivalent. Now I'm using one of the first two formulas to the codiagonal alpha E1 plus alpha E2 diagonal, which is the same thing as the alpha E1 plus alpha E2 by the definition of the binary operation. So this is how you, for example, can obtain all these four formulas. I obtained one, the rest is, other three is more or less the same. So finally, you can notice the following identities. Well, you take the codiagonal, take the diagonal, take the direct sum with the identity, and then take the composition with the diagonal. So this will be the same as the composition of the sum of the diagonal, and then again diagonal. So this is as a maps from the C to the C plus C plus C. And the same for the codiagonal. So this is from A plus A plus A, and this is mapped to the A. So why we need these two observations with the three arguments? Well, because if you have these two, it means if you use the definition of the binary operation, it means that this binary operation is associative. So these two together implies that the plus is associative. Not just do the standard computation, take three extensions, put parentheses in one way and the other way, use these identities and get the same, and show that the operation is associative. And finally, we have tau, which is a map, say, from the A1 plus A2. We'll just take canonical isomorphism, which exists by the universal property. So it switches the place of the first and the second argument. So then this tau is related in the following way with the diagonal and codiagonal. If you take codiagonal tau, this is the same as the codiagonal, and the diagonal is the same thing as the tau composition with diagonal. So you have just simple observations about the universal properties. So then E1 plus E2 is equal to the codiagonal E1 plus E2 diagonal. So then I can insert the tau after the codiagonal. Right, so the tau acting on the E1 plus E2 give me E2 plus E1, but the rest of the formula is the same. So this is здесь?
Нет, чуть ли. Нет, там просто...
Нет, так я пока просто все, что я сделал, это я вместо вот этого вписал вот это вот на этом шаге. А потом вот здесь, вот как, вы как правильно говорите, я как раз это тау применяю и получаю вот здесь И2, здесь И1. Вот. Oh, anyway, so the answer is that this is E1, E2 plus E1. So this operation is associative and also commutative. So we have an abelian group, and also we can notice that well, if you have, for example, short exact sequence A, B, C, and then we have a splitting short exact sequence, so here map phi of B is by definition 0 sigma of B, where sigma is a map from the B to the C. Okay, so let's call the top extension E and the bottom extension, splitting extension, E0. So then from this diagram we can see that the E0 is the zero map on the A, which I apply on the F to the extension E. And E plus E0, well, since this is the same as the identity on the A times E plus the 0 on the A times E, and using formula that we already proved, this is 1 on A plus 0 on A E. So this is 1 on AE, and this is just E. So indeed this E0, which is the product of the 0 and E, is a neutral element for this new abelian group structure. And the proof that the product of the minus 1 on the A and E is the same as the minus E, I'm going to leave it as an exercise. It's more or less the same as here. So let me say that I'm done with the proof of this statement. Okay, so at least we know that extensions form not just a set but an abelian group, and now I want to show that this group is the same group as the X1. To do this, I'm going to construct two maps in one and the other direction. So the problem will be to show that these two maps are well defined, and the fact that they are given isomorphism is more or less trivial from the definition. So let's go in one direction. Suppose I have a short exact sequence or extension E. So this is 0 ABC. And also I fix a resolution. So P is a projective resolution of C. So I'm going to compute X1 using this projective resolution. So then I have beginning of the projective resolution on the top. Then there is also A, B, C. So differentials, D2, D1. So then I can take the identity map on this C, and there is unique up to homotopy lift. Right, so there is a lift. Let me call this. I only need, well, there is only two components. There is alpha 0 and there is alpha 1. So this alpha is just the lift of the identity from the resolution to this exact complex. Okay? So then, since the composition, well, if we look at the composition of the alpha 1 and differential D2, well, you can just think that there is also a map here to the 0, so this composition is just 0. So this is 0, right? But since this is 0, it means that the class of alpha 1 is an element in the X1 CA. So lemma, the map, which I'm going to call psi, from the X CA to the X1 CA, so which is defined, so psi on the extension is by definition the class of alpha 1. So this map is now defined. So that's the map in one direction. Если у вас какие-то вопросы, можете спросить.
X1CA. Что такое просто X1CA? Мы знаем, что такое просто X1, мы тоже в курсе. Что такое X1CA?
Нет, когда мы определяли эксты с индексами до этого, как производные функторы, у них же было два аргумента.
А X без цифры это extensions,
Да,
да?
эксты без цифр — это extensions, которые вот я сейчас на них определил структуру абелевой группы. И теперь я хочу доказать, что на самом деле две абелевые группы одинаковые. X без цифры — это то же самое, что x1 определенный при помощи производных функторов. То есть как бы вот эта деятельность с производными функторами, ну, она вот конкретно для x может быть проинтерпретирована вполне конкретно. Но это на самом деле тоже довольно хорошо, потому что, например, чтобы определить эти производные функторы, нам нужно было, ну, скажем, берем произвольную абелевую категорию, мы не знаем, там есть достаточное количество инъективных и проективных объектов. Но если их даже нету, давайте просто работать с x-тами, вот как я определил до этого, то есть как такие классы эквивалентности. И в этом смысле в любой абелевой категории, по крайней мере, можно рассматривать x1. Вот. Okay, so we need to show this is well defined, and there are two things that we need to check. Well, first of all, this lift, alpha 0 and alpha 1, well, they not unique, they depend, well, they unique up to homotopy. So what happens if I replace alpha by a homotopic map? And then the second thing that we need to check is that this extension also can be replaced by an equivalent extension, and we also need to be sure that the answer doesn't depend on this. Well, first, psi doesn't depend on what? Well, let's say on alpha. Depends only on the homotopic class of alpha. Well, if I have another lift, say alpha prime, then the difference is homotopic to 0, hence there is some homotopy S. Right? So any two lifts are homotopic, it means that we can find such map S with some components. So in this case, there will be, say, S0 here, and there's also S1 here. And there is nothing else, the rest are just zeros. So then if you look at the difference for the alpha with the index 1, yes, alpha prime 1 is minus alpha 1. Well, according to this formula, since we have object 0 here after A, so this composition with A's S1 is just 0, doesn't contribute to this formula. So what's left is just the composition of the S0 and the differential D1. Right? But this means precisely that the alpha 1 prime minus alpha 1 is in the image of the, say, D1 star. And so the cohomology class doesn't depend on this. It was rather quick. Is it clear what I mean by this? Well, you have the differential in the resolution, right? And to compute hom, so that's a projective resolution for the first argument, you take hom from this resolution into A. So this differential induces differential that called differential with the star. And that's exactly the differential that computes the X groups, right? And what is this differential is doing? Well, it's taking exactly the composition with the map by the definition of the induced differential on the homs. So this is precisely meaning that this is in the image of this induced differential on the homs. And since this is in the image of the differential, the homology is quotient by the image, the class doesn't depend. And here you can also, well, here I use the same idea, but you didn't ask me. So if this composition is 0, it means precisely that the D2 with the star of the alpha 1 is 0, which means that this is class in the cohomology, right? Hence this is in the X1. Okay, so this is the property that this doesn't depend on the alpha. And then the second thing that we need to check is that if you have two equivalent sequences, well, the answer is still the same. So let me again draw a diagram with the resolution. We have P2, we have P1, P0, C. So then there is A, B, C. And there is an equivalent sequence A, B prime, C. So here we have 1 and 1. In the middle there is some map beta. So I need to move it a little bit. So this is C here, there is P0 here, and P1 here, P2 here. P0. So these are two equivalent sequences. Say this is P and this is P prime. They are equivalent because they have this map beta, which is an isomorphism. And I want to show that the C of the E is the same as the C of the E prime. Which I think if you just look at this diagram is clear. Right? The class in the X is the same, but because what the difference here, well, this is just identities, right? We want to take this map, right, and take the class of this map. But what you do with the map, if this was alpha 1, then this is just a composition with the identity. It doesn't do anything. So that's about the fine map. Okay, now let's define the map in the other direction. So suppose I have a class of the alpha 1 that lives in the X1 CA. So it means that this alpha, I can interpret this as a map from P1 to the A. The induced differential on the alpha 1, since this is in the cohomology, this is 0, and this is just the composition of the alpha 1 and D2, so that's a 0. So there is an induced map I'm going to call alpha 1 with the bar from the P1 modulo B1 to the A. So B1 is just the boundaries. So B1 is the image of the D2, right? Since the composition of the alpha 1 and D2 is 0, alpha 1 is inducing map modulo the image of the D2. And then I will get a short exact sequence. Чего? Все то же самое, что и раньше. Вот у нас есть дифференциал на резольвенте, он индуцирует дифференциал на хомах, который вычисляет тексты. Ну, мне кажется, надо написать, вы уже несколько раз спрашиваете, вот у нас дифференциал, вот у нас резольвента, P2, P1, P0, C. Так, да? Теперь мы должны посчитать это в резольвенте, применить хом в А, правильно? Соответственно, у нас функтор будет контрвариантный, значит, у нас получится хом CA, здесь будет хом P0A, здесь будет хом P1A, ну и, соответственно, будут дифференциалы, которые будут бить в обратную сторону. В данном случае вот это, например, будет D1 со звездочкой, следующий будет D2 со звездочкой. Да? И что он, собственно, делает? Вот у вас было отображение с какой-то из P0 в A, да? Он просто берет композицию с дифференциалом, здесь был дифференциал D1, берет композицию этого отображения с дифференциалом, и это есть D1 со звездочкой. Так, ну, как бы, так функтор хом работает, грубо говоря. Все. Okay, so now I want to introduce, so that was a remark. Now I want to introduce extension T, which will be just a very simple extension. 0, P1 modulo B1, which is mapped to the P0, and then C. Well, essentially, for this T, I'm just do the standard thing. I look at the resolution, and I truncate this resolution after, well, just one step, and then write the syzygy. So this is the first syzygy of the C. I always have this short exact sequence T. Doesn't depend on anything, only on the resolution. And the extension that I want to use in the definition of the second map is just the product of this alpha 1 with the bar and this T. So set theta on the class of alpha 1 to be the product of the alpha 1 bar and T. So this is a map in the other direction. So theta takes an element in the X1, CA, and produce an element in the X CA, an extension. Okay. So lemma prime, which I think is much easier than the previous lemma, and we I think almost out of time, right? So the map of theta is well defined. Again, what you need to do, you fix the class, and suppose for this class you choose a different representative, but the different representative, what's the difference, is this alpha 1 plus the composition of some map S with the differential. What you need to check is that you consider such map, well, maybe sketch of the proof. So if you consider instead another representative, right, so say alpha prime 1 has the same class as the alpha 1, it means that the alpha 1 prime looks like alpha 1 plus S d1. Okay, so the difference is by the boundary, right? By the boundary, this is, you can think about this as the d1 star applied to the S, right? So difference is by the boundary. But now if you change this map by this kind of additional stuff, it means that the induced map is just a zero map. right? So if you look at this, if you look at this as D1 and then consider this as D1 with a bar as a map from the P1 modulo B1, that would be a zero map. But since this is a zero map, well, you'll get alpha 1 bar plus 0 times t. So this is the same answer. Okay, just check the details. And finally, theorem is that X1 CA is isomorphic as an abelian group to the X CA. Again, I want to leave this as a little exercise, and this is indeed simple. You have two well-defined maps. You just need to check that the composition of the theta and psi in one order is identity, and composition in the other order is also identity. But this is, if you just draw the corresponding diagrams, it's immediately clear. So exercise again, simple one. Okay, let's take a break, and then after break we have the last quiz.